Let's take a look at the west coast of Africa and the east coast of South America. They look like they kind of fit. Is that just coincidence? Or maybe they used to be one landmass and then separated. The question about whether they were together has been a long one. I mean, people have wondered this. They checked fossils on the east coast of South America and on the west coast of Africa, and they matched. But when you take a step back and realize, oh my gosh, Earth's crust moves. And you say, well, at what rate? Turns out it moves. The continents drift on Earth's surface at about the rate that your fingernail grows. That's not very fast in any given moment, but it adds up. And the crust is basically rigid. So if it's going to separate or come together at that rate, eventually tension will build and something's got to give. So either the two landmasses pry each other upwards, you get mountain ranges that way, they can separate, and then you get these sort of earthquake crevasses, or one landmass can, what's called subduct, can be drawn underneath the other as the other one crawls up on its back, basically. So a lot of different things can happen when the landmasses encounter one another. It's because Earth is still hot. We have a combination of heat left over from the formation of the Earth, plus heat sources that come from radioactive elements that are still within the Earth's volume. And radioactivity sends particles out that have energy, particles get trapped, and it heats up the volume, okay? We still have this source of energy, and it is so hot that below the crust, the material of the Earth is not solid. It's like liquid, basically. It is a soft enough solid that it is not stable. And you have convection of zones below it that force land masses above it to respond. If this is what's happening, oh my gosh, in one swing, you can explain earthquakes, volcanoes, mountain building, all in one coherent, holistic understanding of what's going on Earth. This string of islands, there's a hole from the mantle that punches up through the crust. And when that happens, you get the magma, the molten rock, it comes up, and you get lava, and you get a volcano. Then the volcano goes dormant. But you still have continental drift. So what happens? The crust shifts on top of that hotspot. And the hotspot is waiting there to sort of do its thing again, but it's not going to do it anytime soon. You have continental drift, then it's time to be a volcano again. It punches through the crust, makes another island volcano. Then that goes dormant, the continents keeps moving, and you get another one. This is how you get volcanic chains of islands in the world. We have a word for them, they're archipelagos. It's because of continental drift. Tragically, the zones where you have these plate movements, the boundaries, that's where all the action is. That's where the mountains are. That's where the earthquakes are. That's where the volcanoes are. And you can map this in the world where you are more likely than not to expect significant geologic forces to operate. And so, no, it's not an accident that you'll find an earthquake over here and not over there. Or that volcanoes are more prevalent there, but not over here. But by the way, it doesn't mean you would still feel an earthquake, even if you're far away from one of these zones. It doesn't mean your air wouldn't be affected by a volcano that exploded thousands of miles away as the plumes circle the Earth as it enters the stratosphere. No, we're all still affected by it. And especially when you have municipalities that are near these rings of fire, we call them. In those municipalities, it becomes not just simply urgent, but it should be a prerequisite that anything you build in those areas has some resistance to an unstable Earth beneath its feet. In the past, they look at what buildings survived and which ones didn't, and they study those and say, let's build more of those kinds of buildings. Okay? So we can now basically make earthquake-proof, earthquake-resistant buildings, because that's where you're going to die in an earthquake. If you're just standing out in the middle of the prairie and there's an earthquake, No, you're not. You're fine. All right? It's when the stuff we build that we occupy collapses because it cannot sustain the movement of the ground below it. And so you can make buildings where the foundation of the building shifts beneath the building and the building doesn't then move with it. Sliding discs, there's all manners of engineering solutions to enabling a building to survive an earthquake. We're not asking for engineering miracles here. Only design your building so that it doesn't collapse. You still might have to move out. You might have to still rebuild it or re-anchor it or whatever, but you don't want it to collapse. And that becomes the challenge. Earthquakes are very serious when they happen under the ocean rather than on land. It's a pulse of energy that gets introduced into the ocean. That energy has to go somewhere, so it begins to move from the ground zero point, from the epicenter of the earthquake. And as it comes to shallower and shallower land, the size of the wave grows and grows, and thus you get tsunamis. It's one of the primary causes of tsunamis in the world. Oceanic earthquakes, as opposed to land-based earthquakes. Earth is not going to cool off anytime soon. The earthquakes are here to stay. Volcanoes are here to stay. We got to learn to live with them until the day where we have so good at geoengineering that we could just sort of go in the earth and release the stress. Or the volcano's building up pressure, tap it. You know, we tap kegs with spigots. Maybe there's a way to release some of that pressure and control it so that it never blows catastrophically. I don't know. That's in the future of geoengineering. But right now, we're in runaway mode when volcanoes go off and rebuild mode after earthquakes. That's a little bit of what's up with that. I'm Neil deGrasse Tyson, your personal astrophysicist. Keep looking up.